Forces and free body diagrams. A force is a push or a pull. Every force acts on an object, and every force has an agent, which is something that pushes or pulls. In this diagram right here, the agent acting on the football is the person. The person is pushing or pulling the football to cause it to accelerate. Every force is responsible for accelerations. You may have learned this in your younger years by Newton's second law, F equals ma. Forces are also vectors, not scalars, meaning that they have a magnitude and a direction. When you're drawing a force, you want to represent the object as a particle. I know that seems ridiculous, but it really helps those of us who can't draw. So this particle right here is representing a horse or a cow or a planet, or like literally anything you can think of is going to be represented here as this particle. You're going to place the tail of the force vector on the particle, meaning that if you are, for example, drawing something, let's say here is like a box and someone is pushing on the box, you don't want to draw your force like this because the tail of the vector is not on the particle. Instead, you would want to draw your force vector like this. So the tail is located right here. You're going to draw the force vector as an arrow that's pointing in the direction of the force with a length proportional to the size of the force, meaning that this force right here of this length is going to be more forceful than a force of this length. And lastly, you're going to have to label the vector with an appropriate label. Since this is a push or a pull, you might label this as just a regular force applied. So your next question might be, well, if I'm going to label all the forces, what are all the possible labels I could give something? And we will go through those in just a moment. These pictures right here are just reinforcing the idea that the tails of the vectors are placed on the particle regardless of where the force is applied. So you can see over here, here's the person pulling on the box, and you're representing the box as a particle, and you're representing the pulling force of tension right here to the right. The same is true right here. If the spring is pushing on the box, the force of the spring is actually coming in this direction right here, but you're gonna draw it as coming out of the box like that. The same is true over here with gravity. Gravity is pulling downwards on the box, so you want to draw that as a particle with the arrow pointing downwards representing gravity. You can combine several forces to make a net force, which is also called a resultant vector. This net force is not a new force. It's going to replace all of the original forces. What does that mean? Let's take a look over here at example A. You have a top view of a box and two ropes exerting tension forces on the box, one of which is pulling upwards like this, and one of which is pulling downwards like this. If you wanted to combine them together and find the resultant vector, what you would do is you'd take these two forces, add them together tip to tail, and then the resultant vector, you might remember, points from start to finish. And the resultant vector is the vector sum of all the forces acting on the box, and it's showing the direction the box might actually move were those forces applied to it. So you can either draw your box like this, with two forces pulling on it, and that's actually equivalent to drawing a box with a force like this. This it would simply be labeled as the net force, or the force net, right? This, and this guy would be labeled, for example, as force tension and force tension. You can see that this net force right here is not a new force. It's simply replacing the original forces, this and this, that were acting on it. And you'd have to label it as so, which is why it's labeled as force net. There are two major categories of forces: contact forces, which are going to act via physical contact, and field forces, which are going to act at a distance as part of a gravitational field or an electric field or a magnetic field. So we're going to start off with contact forces, which are acting via physical contact. The first of which is just the generic force applied. You can see it represented as F for force, little a for applied, and that's just going to be a general push or pull. The force of tension, you can see there's a little T right here for tension, is the pull of a string or a rope or a wire. That's because you can't push on a string. If you try and push on a string, it'll just collapse on itself. So tension is always a pulling force, and tension is always going in the same direction as the string or rope. The force normal is the weirdest one, I think, out of these, and kind of the hardest to wrap your mind around. It's the force exerted by a surface against an object pressing on it, and it's responsible for the solidness of a solid. So what does that exactly mean? That means that, like, let's say you have this college physics textbook resting on a table. If you were to represent the forces acting on this physics textbook, you might say, all right, there's a gravity acting downwards, this being my gravity. But if you only draw the gravity arrow acting downwards, you're implying that your object is having a net force downwards, and that means it's accelerating down towards the center of the Earth. And this textbook is obviously not doing that. It's just chilling on the table, which means there has to be an upwards force that's equal and opposite, and that upwards force has to come from something. And in this case, the upwards force is coming from the particles of the table itself pushing backwards, the compressed molecular springs pushing upwards on the object. So what's actually happening is that the table itself is pushing back. And that is your force normal. And the force normal is typically going to be equal and opposite to gravity in the direction that's perpendicular to the surface. So if your object is not flat, it's not going to be perfectly equal and opposite to gravity. And we will explore those situations in a later lesson. The force of a spring, labeled as F spring, is the force created by a spring. This direction depends on the situation, and it's opposite of what you might imagine. So you can see over here, if you're stretching a spring, let's say you have a person pulling this way on the spring with all of their might. The spring actually is going to act in the opposite direction, pulling back. And if you're compressing a spring, if you're like pushing on the spring with all your might to compress it, the spring is going to push back in the opposite direction at you. Friction is also going to act in the opposite direction of your motion. Friction is the force exerted by a surface to oppose motion. Drag is specifically friction applied by a fluid, such as air or water, like air resistance or the resistance of water as a boat cruises through a lake, something like that. We are actually going to ignore drag in all problems unless specifically indicated. The last example of a contact force would be the force of thrust. This happens when a jet or a rocket engine is expelling gas molecules at a high speed, and they're always going to be in the opposite direction of your exhaust gas. So if you're producing a lot of gas down this way, your thrust force is going to be in the opposite direction. This is a prime example of Newton's third law. For every action, there's an equal and opposite reaction. Field forces are forces that act on an object without physically contacting them. For example, weight. Weight is labeled right here as the force of gravity. And it has typically the acceleration of gravity, 9.8. So if you're calculating it as F equals ma, which is Newton's second law, the acceleration you see for weight is typically 9.8. This is considered the gravitational pull for objects that are on or near the Earth's surface. There's an entirely different gravity equation for objects that are way out in the universe somewhere or off of the surface of the Earth. But for objects that are close to the surface of the Earth or on the Earth, we're going to use force equals mass times acceleration to calculate it. Gravity always pulls downwards. Even if, like, for example, let's say that you have a pendulum and your pendulum is like swinging like this, even at like this point right here, even if the tension, for example, is pulling this way, your gravity is always going to be pulling directly straight down, regardless of which direction it's moving. These last examples of field forces, such as the magnetic field, the electric field, and the nuclear field, we're going to ignore these until much later in this class. So these will come back around. Just know that they're examples of field forces that can act on an object without physical contact. We're going to do a few examples of free body diagrams so that you can practice drawing that particle, attaching the tail of the forces to the particle, and labeling all of your forces. So we're going to start by drawing a free body diagram of all the forces acting on the chair. Let's start by imagining which forces are acting. There are 4, so stop and think about that. Which 4 forces are acting on this chair? The first of which you might imagine would be acting downwards, your force of gravity, and equal and opposite of that, acting upwards, is your force normal. I'm going to draw these lines on it to indicate that they are equal. The next force you might imagine is the force of a push or pull, and you can see that this guy is pushing in this direction. However, that's not the way we draw free body diagrams, right? Remember that the tail of the object has to be the tail of the vector has to be attached to the particle representing the object, meaning that his push instead would be represented like this, his force applied. And the last vector you might consider is the force of friction. I know that in real life that friction is acting this way, resisting the motion, but once again, remember that we have to draw it with the tail of the vector connected to the particle. So you would draw, for example, his force of friction like this. Lastly, pay attention to the length of these 2 vectors right here. So if they are drawn equal length, that means that the forces are canceling. It doesn't mean the object isn't moving. It just means that the object is not accelerating. So if there's no net force, it can move. It just can't accelerate. So if these 2 are equal length, that means it is moving but not accelerating, or it's not moving at all. If one of the arrows is significantly longer than the other, that can show that it is moving and accelerating. Let's do a few more examples to solidify this concept. It says a 10-kilogram box is pulled across the table to the right at a constant speed with a force of 50 newtons. These are the forces acting on our object. I'm going to label this guy 50 newtons. And it wants to know what is the force of friction and what is the force normal. The key to answering this is that it's moving here at a constant speed. So that means that all of our forces are canceling. So since force equals mass times acceleration, if there is no acceleration, there cannot be any net force, meaning that they all have to be equal. So if this is 50, that means that this force of friction also has to be 50 newtons. You can either write it as negative 50 newtons, or you can write it as 50 newtons to the left. Next, we have to calculate our force normal. Our force normal is going to be equal and opposite to our force gravity. So calculating our force gravity is going to be the mass of the object times the acceleration of gravity. And the acceleration of gravity is 9.8. So our force gravity is going to be 98 newtons downwards, which you can either write as 98 newtons downwards or negative 98 newtons. That means that the force normal acting upwards has to be a positive 98 newtons. These next few examples we're going to just draw without calculating. So take a moment and see if you can figure out how to draw the free body diagrams for each of these. I'll pause for a second, or you can pause the video for a second and see if you can draw these. And I will go through the answers in 5, 4, 3, 2, 1. Hopefully you've had a chance to pause the video and draw what you think are the forces acting on each of these objects. Here we go. You have a mass suspended by a string. This guy right here is your force tension, because strings provide a tension force. You have gravity acting downwards, and these two are going to be equal lengths if it's hanging suspended. Let's try the next one. This next one has a force gravity and a force normal, equal and opposite in length, showing that the object is not accelerating, it is at rest. This next one always weirds me out. It weirds me out that the diagram of an object sliding at a constant speed is exactly the same as the diagram of an object at rest. And that makes sense because neither of them have a net force, because neither of them are accelerating. But you might wonder, how can I tell the difference between these two? Honestly, you can't, unless someone comes through and like puts an indication that it has a velocity in some particular direction, which sometimes they do and sometimes they don't. If someone has graced you with a little velocity arrow, you know the object is moving. Otherwise, there's no way to tell from the diagram whether it's moving or not. An object sliding at a constant speed with friction, once again, has to have all of its forces canceling out because it's not accelerating, it's moving at a constant speed. So that means your normal and gravity are equal and opposite, and your applied and friction are equal and opposite. This next object is accelerating with a string, so it has a force tension instead of a force applied. And since it's accelerating, that means there's a net force, which is why this line is so much longer than this line, to show that there is a net force in the rightwards direction provided by the string. On a frictionless surface, it might look like this. You might have, once again, these normal and gravity forces canceling out. And then over here on the right, you have this tension force. This tension force has no opposing force in the opposite direction. So the fact that this tension force here is unopposed means that it is accelerated to the right because it has a net force. Good work, you guys. See you next time.